All right, it looks like we are live here. Maybe I'll wait a few beats as people find their way to click into this spot. Not too many beats though. Okay, so let's begin our second keynote session of the virtual workshop. I'm very glad to have Andreas Rossberg here. I'm sure many of you know him from his longtime participation in the POPL community, starting from PhD research in functional programming, number of contributions in module systems and modularity in programming languages in general. He was a postdoc researcher at the Max Planck Institute, then joined Google, where I believe he kicked off the work that this talk will be focusing on the WebAssembly language standard and various implementations of it. And since then, he's moved to the Dfinity Foundation. And I think that's about enough for an introduction. Really interested to hear what he has to tell us about WebAssembly. Thanks, Andreas.
Yeah, thanks, Adam, for the introduction. So yeah, Adam asked me to give a talk about WebAssembly, like including technical aspects, social aspects as well, which is quite a bit of ground to cover. So I won't be able to really go into depth in any of this, but I try to cover some ground here. And maybe halfway through the talk, I will kind of give a poll for what kind of direction to take for the rest of the talk, because I have two different things I could talk about. And yeah, so this is supposed to be sort of like more workshop, more interactive kind of thing. So please feel free to interrupt me with questions at any time if something is not clear that I said. And Adam will then just let me know, because I only see the presentation screen here. Okay. Oh yeah, and I apologize that I completely dropped the ball on providing an abstract actually for this talk, but I hope you will still enjoy it. I just realized earlier today that I forgot sending you that. Okay, so I'm talking about WebAssembly, and I'll have to start with kind of what is it, right? I assume these days most people have heard of it, but there might still be some only vague idea of what it is. So the original pitch that you probably have heard is that it is like, it's a new code format, which is supposed to be portable and which is supposed to give you like more or less native code performance, something in the ballpark of native code performance in your web browser or in all web browsers, right? So that was the original kind of marketing about it and motivation and so on. But I would ask you to just mostly forget about this. What it really is it's a virtual machine, and particularly a low-level virtual machine. It is fully sandboxed, something I unfortunately won't be talking about this time, but it has a lot to do with its module system. And it can be embedded pretty much anywhere where you want a virtual machine. And it has been used in many places. It has been embedded in many places. So obviously there has been the web where it all started, but it's also being used in edge computing. It's used on several blockchains. It's used in cloud, mobile, on embedded devices. Apparently there are various people interested, including myself, using it as simply a standalone runtime, if you want, and many other applications you could imagine. So really, the whole name is pretty much a misnomer. That was more like a marketing thing, if you want. And part of my mission is to make it even more a misnomer. So just to give you a quick glance, if you have never seen WebAssembly for real, here's just one slide to give you a vague idea. So imagine some pseudocode like this, which is just a factorial function, very easy one. So this is roughly how you would render that into WebAssembly. So, and there are some things you can see here. So first of all, WebAssembly is a stack machine. So you can see that here, so these 4 lines are kind of roughly this function call. So you would have the local get instruction, which pushes the value of the function parameter onto the operand stack. It pushes a constant, then it performs a subtraction, which pops these two operands and pushes the result. And with that, it calls recursively the function. The function itself has parameters and results which are typed. So WebAssembly is a fully typed language. You also see here that it has some form of structure control flow, actually, in the form of the if then else block-like statement here. And there are a couple of others like that. And one other thing you see here is that the whole, well, first of all, the code is organized into a function, and there can be many of those, so that may not be that surprising, but functions themselves, plus some other things you can define, all grouped into a thing called a module. And the module can export some of the things it defines. Like here, it exports the function we actually have defined under some name we can pick here. So a WebAssembly binary is actually a module. And instantiating or loading a binary is actually linking. And a WebAssembly application can consist of many modules that you link together. And what I'm showing here is obviously is a text rendering. It's the official text format of WebAssembly, which is like this nice S expression format, which I annoyed everybody with. But of course, the way it's actually deployed is as a binary. And then this function, for example, would look like this. So it's some bytecode we have defined. And every binary is just one WebAssembly module. So when you see a .wasm file, that is really defining such a module. So yeah, just to give you an idea roughly what kind of language this is, not a very sophisticated example, but you see what it is. So yeah, this is supposed to be a bit of a background talk as well. So I wanted to go into some of the history of how WebAssembly came about. And I could easily fill an entire talk with this, so it will be just one slide, rather superficial, but it might still be something you didn't know. So zoom back to the year 2015 is roughly when it started. Maybe it was late 14 even already. So at the time, JavaScript on the web was everywhere, right? So JavaScript had the monopoly on the web. More and more complicated applications were written in JavaScript on web pages. And of course, there was a significant subset, or there still is a significant subset of web developers that were not happy with that situation. They wanted to work in a better language. So many compilers appeared that target JavaScript, compiled to JavaScript. But JavaScript is not only horrible as a language to work with, at least in my opinion, it's also horrible as a compilation target for many reasons. So it wasn't an ideal situation. And at the same time, there were like all these engine developers, so teams who actually built JavaScript engines in the browsers. And I was one of these developers at the time. And we were also frustrated with JavaScript and the insane amount of complexity and effort it took to make it run fast, and the insanely complex artifacts that we built there. And even worse, to support some of these compilation patterns that people had come up with to run fast and so on. It just seemed so much effort going into like doing this work, like hundreds of man-years. All this energy that is wasted in every computer for optimizing JavaScript over and over again while it runs, and just to work around its deficiencies. So that all seemed like that should not be the way it's supposed to be. And of course, at the time, there were already some kind of solutions that trying to address this problem. So Google had a NECL native client that was a way to deploy x86 code, binary code to the web, but it only worked on Chrome. Mozilla had something else, which was called ASM.js, which was a very stylized subset of JavaScript defining something that an engine could optimize better, and which a compiler could target as a kind of machine code. But both these solutions were pretty complicated. They didn't scale well, and they were lacking in various ways. So, of course, all the browser like vendors, the engine developers, the teams, they all knew each other, right? We were talking with each other and so on. So we shared common sentiment here. And some of us were starting to talk about like, yeah, maybe we should just try building something better instead of hacking around it. And so a couple of people, I should particularly mention Luke Wagner from Mozilla and Ben Titzer from Google, who really started like just building something. And this initially was completely under the radar of any management in these companies. But it caught on pretty quickly, and they managed to convince not just their own management, they also convinced other browser vendors, and those were the big four at the time, like Google, Mozilla, Apple, and Microsoft. Now it's down to 3 of those. To participate in this effort and actually make it real. And so it was just like a few months, and we created this working group and started working on it for real and implementing something. And I'm still amazed how fast this happened and that we convinced management, because they were pretty skeptical at first, because they were just thinking in terms of JavaScript, right? Anyway, so this is kind of how it started, how it came about. And we wanted to create something better, as I mentioned. So we obviously had a number of goals in mind, and this is the slide I always put on for this. So, but also some constraints we had to meet. So first of all, yeah, one thing we wanted to do better than previous attempts of doing virtual machines is we wanted it to be completely language independent, right? So basically all the popular VMs, mainly the JVM, .NET, and you could also count JavaScript into this, they were very particularly tailored to a given language with a complicated object model, so mostly object-oriented languages, and not particularly well suited for compiling other languages that didn't fit this model well. I mean, people did it anyway because there wasn't much else they could do, but it's not ideal, right? So WebAssembly is really supposed to be neutral, and that's why part of the reason why it's a low-level virtual machine. So it does, unlike these other VMs, it does not abstract a specific language. It abstracts the hardware. So we're coming from the other end, right? We're just trying to be as thin as possible an abstraction layer over common hardware. And then a compiler can do whatever they want, and they just build more or less a regular backend for this virtual architecture. At the same time, this architecture is supposed to be independent of concrete hardware, of concrete environments. And of course, it ought to be fast. It has to be safe. And we also wanted it to be very well defined, right? So, which means mostly deterministic, and so that you can reason about it in the same way. And this is, again, something that is not necessarily the case when you look around in other like low-level languages. That is not the case at all, right? They're usually not very well defined. But all these things, so these things are just one dimension, if you want, for designing such a language, which is about semantics. There's another dimension here, which that might be less obvious when you're more from a regular programming language background, which is representation. So this is for code in environments like the web, where code is transferred over the wire, right? So it really matters that, for example, the code is compact, right? Or you want a format that is as compact as possible. And if you're aware with the JavaScript world and the amount of the length people go to save bytes and to minify JavaScript just to save bytes, then you know how relevant this is. We also wanted to be easy to generate. So if you have a compiler targeting it, what we call a producer, it should not have an unnecessarily hard time. And dually, an engine, the consumer that has to decode that format, should have an easy time as well, and should be able to do it fast and decode it fast, validate it fast, compile it fast. All these things should be possible to do fast, right? So for example, the type system, so the validation of JavaScript, of WebAssembly, sorry, is really was intentionally kept very simple so that you can decode it not just in linear time, but with basically download speed, right? So it's basically unmeasurable when you download a binary and compile it. And there are further considerations for making downloads even faster, or like startup times in a web page, for example, which is that you want a format where you can already start compiling even if you haven't download the whole thing yet, right? So it's supposed to be streamable, and beyond that, you want to be able to even compile multiple parts of it in parallel, like several functions you can compile parallel to each other to drive down startup times even further. So startup times, latency is really a big thing, especially on the web. So all these were considerations that went into WebAssembly, and I claim that none of the pre-existing technologies met like even half of these requirements the same way WebAssembly did. So those were kind of like the more technical goals, but we also had a whole list of like secondary goals, or maybe you could call them hidden agendas to some extent. So, well, one pretty open goal was that it's supposed to be an open standard. So we really wanted its entire development to be open and not repeat the sad history of things like Java, where you have companies suing you over using it in certain ways. So no patents should be involved, no copyright issues or whatever. That was really important. It was a primary goal. We also we're very interested in not making it web specific, right? So most of us working on JavaScript actually had some more general language background, and weren't particularly interested in just inventing yet another web technology. So that was just our excuse, essentially, the web. But we really wanted to build like a universal VM. And for example, the specification, the language standard, I think doesn't even mention the word web. So it was very carefully designed to not depend on the web in any way whatsoever. Yeah, and we want a principled design that should not be surprising, really apply all the lessons learned in 50 years of programming language practice and research. And part of that was actually making its specification better than what we have seen before. Some of us were very frustrated with the state of the art of language definitions at the time, right? Most of the language definitions out there basically consist of some prose, some nice sounding sentences, and hoping that they make sense. And often enough, they don't. So we really wanted to raise the bar of for that and have a much more precise and accurate and complete specification. And as part of that, we were interested in applying all these formal techniques that research had shown us and had developed over the last 3-4 decades, right? For specifying languages properly, how to do it right. And we wanted to show off that these techniques actually work, even in the real world, and they could be used for real world languages. And another part of that motivation, especially for me personally also, is that I wanted to provide something that is like ready for academics, for other researchers to pick up. So, and not have to repeat this thing that you have seen with other languages or similar technologies, where first thing is people have to make a career out of like reverse engineering the language and its semantics and formalizing it after the fact, right? We wanted to have that formal semantics right there from the beginning, so people can just pick it up and do something with it for research. So in a way, you can sum all that up, that we were really interested in getting out of the 1960s, which from my perspective is where most of at least real-world language technology is still stuck in terms of how it's specified and defined, and leap forward for like, I mean, at least into the 90s or something. And personally, I cannot not mention that is one thing that definitely inspired me here was this book. I'm sure some of you have seen that. When I was an undergrad student, that like just blew me away, and I was since then wondering why not everybody is doing it like that. And here was now a chance to kind of put that into practice, design a new language that tries to be as good as the definition of standard ML in terms of accuracy and precision and so on. So I'm really grateful to have stumbled over that book at the time, and it has inspired me ever since. And I hope we managed to do something similar. So yeah, there's a formal semantics for WebAssembly. That's kind of the summary of what I said so far, and it has been there from the get-go. It was an inherent part of the design process. It was designed hand in hand with the language itself. And one outcome of that is that WebAssembly has no undefined behavior, right? So it's a well-defined language. As I said before, that's actually not a small feat when you look at other low-level languages or compiler IRs, be it C, be the LLVM bitcode. They're all riddled with undefined behavior. None of that exists in WebAssembly. Everything is well-defined. And not just that, we also have machine-verified proofs of that. So the semantics is actually mechanized, and we'll get back to that later. And I would argue that this kind of feedback loop with formalization led to a substantially cleaner and simpler design in the end. And I can substantiate that at least in terms of like how small the semantics is. And moreover, this formal semantics was not just supposed to be something like we write on paper and have in the background somewhere where it rots. It was supposed to become an integral part of the language standard, and it is. It's really the entire language specification is structured around the formal semantics. So, well, when you define a language, I guess you all know what you have to do. There are basically three parts to it. You have to define syntax, static semantics, and dynamic semantics. And to do so, you have to wire these three things up through abstract syntax, right? So you define some abstract syntax and define a way to turn the concrete syntax into that. And then the semantics is defined in terms of the AST. So that's what we did for WebAssembly. So there's an abstract syntax, as you would expect, it's defined by some context-free grammar, and the kind of terms we're dealing with here is just sequences of instructions. So a program really is just a list of instructions. There's actually some structure to it because of structure control flow, so it is really nested in some way, but yeah, first approximation is a sequence of instructions. And there are some additional instructions that you don't see in the source language, some administrative instructions which I had to add to deal with some of the reductions, like, for example, to represent labels. But mostly it's just the source language in AST form. And here is basically the entire abstract syntax of the initial version of WebAssembly. So this is from our PLDI paper. You can see it's quite simple. I won't go through all of that, obviously, but there are just like these 4 types, right? So remember, it's really abstracting the hardware. So you only have number types. There's nothing else, right? You have integers and floats. That's it. You have various instructions, for example, to push a constant, to do binary arithmetic operations, like here, some control flow and so on. You have ways of defining certain things in a module, and ultimately you have the module, which is just a list of definitions of functions, of imports and exports, and some other things I won't go into here. But that's really all there is to it. The main thing is really instructions. And that's what you define the dynamic semantics on. So, and as you would hope and as you would expect, that's defined by structural operational semantics with small step reduction rules, right? That's how you should do it in 2020. And reduction is defined on configurations. So configurations are sequence of instructions and state. And there's also a frame component here, which captures the current function and module you're running in, so you are able to access some of the local definitions. And then the reduction relation is, yeah, just reduction over these configurations. And we define reduction in the standard, in the way that's standard nowadays with evaluation context. And the evaluation context is really just a hole in a sequence of instructions. With the additional property that all the instructions left of the hole are constant instructions. So when you define a reduction semantics that way, you usually define like your subset of terms, which are your values. In our case, the values are the constant instructions. So those that just push a constant to the stack. Those are our values. And essentially, you can read this as like, you know, the values left of the hole, that's your operand stack. That's what you have pushed on the stack currently. And the right is the remaining instruction sequence. And you terminate when all that is left is are these value instructions. So then the values they represent are the result of your computation. So WebAssembly allows multiple results. So that's why you just have a stack essentially. And by doing it this way, so like not even representing the stack as some explicit thing on the side, just defining it as part of the regular syntax, you can just immediately apply all the syntactic soundness techniques that you're so familiar with and do the proof in a completely standard way. And yeah, again, here's like a snapshot from the paper, and this is the entire reduction semantics for WebAssembly. It's like 1 page. Now it's a bit more, but this is like was the version 1.0. And I hope you can see if I zoom in here. So just to show, like, for example, here's the reduction rule for binary operators. So you could imagine the T being I32, so in 32-bit integer, bin op being add. So this would be an addition on I32 ins, and it would require 2 constants on the stack, essentially 2 I32 constants, and it pushes 1 new constant. It replaces the sequence with the 1 new constants computed from the binary operator. That's really it, and various other things to define in a similar manner. And then you have, well, it gets more interesting with control flow and so on. I have actually slides for that, but I suspect that in the interest of time, I probably have to skip over those. But this is essentially where you introduce some of these administrative instructions to record the label and record the continuation of a label. But yeah, I'm sorry, I have to skip over that because I'm using more time than I thought. So then the other part of semantics is the static semantics. Again, everything is kind of like as you would expect. You have a typing judgment form for typing instructions and instruction sequences. The context there just records the bindings in the current module and the locals and labels in your current function, and you type it with a stack type, right? So that denotes what you're popping off the stack and what you're pushing onto the stack after you have finished. So kind of the diff for the stack. And you can see, I hope, how that composes if you have multiple instructions or instruction sequences and just concatenate them together. Can just compose these types transitively. Plus, if you add some weakening rule properly. And yeah, here are some typing rules again for blocks and loops. As before, I will skip over this and just show you this again. Like these are this is the entire validation of WebAssembly. It's like 3/4 of a page again, and it's pretty straightforward. I mean, part of that is because it's a pretty dumb type system. But even then, it's like one comparison point, one data point for comparison would be, for example, the JVM and its bytecode verification, right? So it's not entirely a fair comparison because JVM is a bit more complicated with its object model and everything. But still, the JVM bytecode verification, the specification of that in the language spec takes 160 pages. So no amount of extra object system can justify that it's more than 2 orders of magnitude bigger than what we have here, right? Because at the core, it's still doing something very similar, like just going through the bytecode and trying to check that the stack is always well defined and well typed. So I think this is really demonstrating the value of formal techniques and their positive benefit on getting a clean and simple design. Because if you do that retroactively, then you inevitably end up with a mess, I'm pretty sure. I've never seen a counterexample to that. Yeah, and kind of the final piece, just one slide here, is parsing and decoding is something we also actually formalize in the spec. And we do so by using an attribute grammar. So the text format is defined by just some grammar with attributes that synthesize the actual AST. And exactly the same for the binary format, because the binary format is just defined by a grammar as well. It's just completely regular grammar, except that your tokens are bytes, right, instead of some textual tokens. But other than that, it works exactly the same way. And here's, like, for example, the excerpt from the grammar for instructions, where the first byte is kind of the instruction bytecode, and then you have some immediate sometimes. And here's the attribute that gets synthesized, so a term in the abstract syntax. Okay, and the final piece here is mechanization. So all this is on paper, but of course, state of the art now is to mechanize. So there are several mechanizations. One is kind of not really counting, but I mention it anywhere here because that's kind of how I started. So my first contribution, practical contribution to the project, actually was writing the prototype interpreter for the thing in OCaml. And I wrote that in a very declarative fashion, basically anticipating the formal semantics, right? So I then wrote the formal semantics by transliterating the interpreter into reduction and typing rules. But that only worked because I already wrote the interpreter the way that I envisioning how the typing rules and reduction rules would look, what they would look like. So that was kind of our, in a way, if you want to stretch it a little bit, an executable version of the formal semantics. But of course, you can't directly prove anything about it. So that was done then by Konrad Watts. So I did the paper version of the semantics, and we wrote the paper for the PLDI paper and submitted it. And I was hoping somebody would pick it up and mechanize it, because at the time I didn't have the means to do that, time to do that. And I was fortunate enough that Konrad Watt immediately jumped to it and went away. I showed him the paper, and he went away for 2 months and came back with a complete mechanization and a verified interpreter and so on. And that was great, because doing so also uncovered a couple of minor bugs in the paper version, so that we could fix them before the final version. But I mean, Isabelle is great, but for various reasons, people usually ask for a COG mechanization, and it took a little bit longer until we got one there. And so that was done by the WebAssembly project. A bunch of people, again, Konrad Watt being the main guy behind that, and some others like Philippa Gardner. And that has been published last year. So there's now a full COG mechanization as well, and you can hook it up to projects like Iris, I think, and do all the sort of formal reasoning in a theorem prover about WebAssembly in the future, hopefully. Yeah, and I already mentioned that. So having a mechanization even early on was also helpful, because we could fix some bug, and it definitely increased the trust in the correctness of our specification. Yeah, and finally, I already said that the standard is really structured around the formalization, but here's where you have to do a compromise, right? So I could not just write the definition of WebAssembly in the way the definition of standard ML worked, because just having formal rules would just not fly with people, right? So what I had to do is I also had to add prose that people could read who are not PhDs in programming language theory. So basically the prose was just a text rendering of the formal rules. So the rules were first, and the prose was second. And they are kind of side by side in the specification, and you can see how they relate to each other. And that is, even if you don't care about the formal rules themselves, it's still valuable, because it gives you much better eyeball proof, or eyeball way of checking that the prose is correct, because it has to correspond to the rules. And if it doesn't, you should wonder why. Yeah, and that is online if you want to take a look at it. Right, so now we have this nice thing, right? And we managed to kind of push the boundaries of how you can do things in the real world, I think. And we want to keep it that way, right? And the development of WebAssembly is by no means done, right? So there is, actually should go here first. There was initially, the first version we shipped was initially kind of limited to supporting low-level languages. That was our first use case where the most pressure existed to provide some solution. So we initially deliberately limited the goal to support those well. And then obviously, since we want to move beyond that, and that's what we have been working on in the past years, adding better support for high-level languages. And maybe in some distant future, or there will also be support for dynamic languages, whatever that means. But yeah, I don't know when that will be. But anyway, so oops. So there's an ongoing evolution, and we have a quite elaborate process for that to ensure that the quality of the implementation, the specification, and the design in general is preserved. I mean, first of all, I should mention that the whole proposal process is open, right? I already mentioned it's an open standard. So anybody can participate in this process. We have bi-weekly meetings. All the discussions are on GitHub. Anybody could join in with no prerequisites whatsoever other than just registering. So really, anybody could bring up a proposal if they wanted, and if they managed to convince some people that this is interesting. But eventually, you will have to come up with some deliverables. So there's a process, and it consists of several stages. And in different stages, you have to come up with some different deliverables. So one is maybe the most obvious one. You have to include the spec text. At some point, you have to write the spec text. But you also have to come up with the actual formalization, right? It's part of the specification, so you have to produce it. Or if you can't, you have to find somebody who can do it, or convince somebody else to do it for you. You also have to extend the reference interpreter, which is part of the same GitHub repo with the new features, and that has to mirror the formalization one-to-one, supposedly, so that we have some trust that it's doing the same thing. You have to come up with a comprehensive test suite that has to run on the reference interpreter and that all others can use as well. So there's a whole like special text format for writing WebAssembly tests, and you have to extend that. And finally, you have to find a minimum of 2 engine vendors who do WebAssembly production engines and convince them to implement your feature so that there is enough trust that this can be implemented in a production quality system properly. So all these things you have to deliver before a proposal will land in the standard. And of course, you also have to convince the working group that it's a valuable feature. So there will be a vote in the end, but they won't even vote unless you have done all this work. There are 1 or 2 things here which are not on the list, and that is somewhat unfortunate, of course. So I say here you must extend the formalization. Unfortunately, that does not mean that you have to extend the proofs, right? Because that is not something we can realistically require at this time from a broad population. And similarly, this doesn't mention the mechanization, right? So I would love to live in a world someday where all these things require you doing a mechanized formalization even, and extending the proof of soundness. But I think that's way too much a leap at this point to even consider. But that is kind of my ideal world where I would want to live in eventually. All right, and I skipped over that slide. Okay, so there's not that much time left. So maybe at this point first, I was talking a lot. I don't know. I wonder if there are questions so far. So maybe this is a good time to interrupt for questions.
While people are thinking about their questions, let me start with one. Your description of the proposal process talked about needing to get enough vendors to implement the feature. Mm-hmm. There must be some sort of somewhat formalized process to decide who is a serious enough vendor to count for that purpose. How does that work?
So what the document actually currently says is not production engines, but web engines. And that is a bit controversial, and I think we should change that. But basically, there is maybe a handful of engines that are considered like mature and high quality enough to qualify. So those are the main 3 web engines, which would be V8, SpiderMonkey, and JavaScript Core, so the Safari engine. And there is WasmTime, which is a pure WebAssembly engine. But so far, the proposals we have landed so far basically always were validated through SpiderMonkey and V8. And the fact that like that Microsoft doesn't no longer have its own engine is not really helping.
Right.
So yeah, this is a bit, this is where it gets slightly political at times. It's a good question. And not everybody agrees on what the precise criterion should be.
Yeah, okay. Let's see. Folks, feel free to post text questions in the Q&A section, or even press raise hand if you'd like to step onto the stage and ask a question. Let me try one more, which I guess just confirm my understanding that you mentioned it's I forget which adjective you used, a simple type system here. My understanding has been this is kind of a one level or a flat model of memory safety or isolation, where you have a sandbox and you want to make sure it stays within the sandbox, and you enforce no modularity within the sandbox. Is that right, as a description of the goal?
Right. So one thing I didn't really get into is that the memory model you have here. So you essentially have this notion of a memory that you declare or define, which you can also import and export. But if you do so, it's just one linear raw byte array that is so address space that is shared between all the modules that import export it. And of course, everybody can step on their own or their other feet. So you don't have any protection within the sandbox.
Right.
There is, however, one of the big proposals being worked on right now is the GC proposal. And that would add a much more sophisticated type system where things are allocated on the engine's internal heap. So it's not in linear memory, it's another thing. And it's garbage collected there. And that immediately, of course, requires much more complexity in the type system. And like you really have type pointers essentially. And you need to know the structure of all the things you're pointing to and so on. And of course, the engine then has to guarantee that you can't like access beyond an array bound, for example, or struct. So if you were using that in the future instead of linear memory, then you would get more safety even within the sandbox if you want.
Okay. Sounds good. And in the meantime, 2 more questions popped up. So let's look at one of them here. Kartik wants to know basically what worked and did not work here for involving this kind of formalism and mechanization with the real world language spec.
What worked and what did not work?
What would you suggest to other developers of real world languages in terms of if they were starting from scratch, what should they do based to learn from your experiences?
So I mean, to be fair, for WebAssembly, it was comparably simple because it's just such a simple language, right, in terms of the type system and the general structure of it. I can't think of anything specific that did not really work well on the technical side. It was, once you got the right ideas, it was relatively straightforward to write down. I really didn't have to think hard about much at all. That would definitely, I presume, be different for a more complicated user-facing language, right? So, I mean, WebAssembly is not really a user-facing language, so there are quite a few things, complexities we don't have to deal with. But yeah, I don't know. I mean, it's hard to extrapolate from such a kind of maybe even somewhat degenerate example, if you want. But the most important part for me definitely is, which I think this proved, is that you have to consider it from the very beginning. If you just start too late with trying to formalize something you already have and that's already gotten complicated, then you will have a hard time. You really need to have this feedback loop the entire time, I think.
Makes sense. All right, on to the next question. So the next one that popped up was Zhang's question about how WebAssembly supports calling external library functions and how to ensure safety in that case.
Right. So I only briefly mentioned the module system and that it has imports and exports. And essentially, the way sandboxing works in WebAssembly is that a module by itself can't do anything, right? You have an instruction set, so you have a virtual CPU, that's all you have. the only way you can interact with the environment is by importing something. And then it becomes kind of dependent on the host environment, what that means. So in the case of WebAssembly on the web, what you can import are JavaScript functions. And when you import them, you can call them as if they were WebAssembly functions with some type conversions going on the boundaries. And then you can just do whatever JavaScript can do. So you basically can escape into the JavaScript sandbox that way, right? But only if your module is linked that way. So there has to be the site using your module has to link it, which means it has to provide these imports. So it can sandbox them by providing whatever capabilities in terms of in disguise of functions it wants to provide, and is in full control of that. And of course, in other environments, that they would have to define how they do it. So this is kind of then external to the language itself, right? What host functions are. So the specification has this abstract notion, axiomatic notion of a host function that can do certain things, but is otherwise not specified. And then it depends on the embedding environment to fill in this definition, actually. I don't know if that really answered the question.
At least made some progress towards answering it, yeah. Safety is a word that has a lot of definitions.
Right, so this axiomatic definition at least requires that all the mutations to the WebAssembly state themselves are sound with respect to WebAssembly. So it can't break the WebAssembly's own soundness. But I mean, ultimately, that is an axiomatic assumption that the specification does, and implementation would have to implement correctly, right?
Right.
At the boundary.
Okay. And I see at least one more question from the audience. Boss wants to know, how would you motivate WASM for blockchain applications compared to other VMs that are out there?
Right. So one of the big ones is that it's fully defined and fully deterministic, or at almost fully deterministic. So for blockchain, it really matters because you have this consensus protocol, you replicate computation, right? And you need consensus on that in the end. You really need determinism. It's like totally essential. And WebAssembly is deterministic, except for float nans, but you can easily make that deterministic too if it matters. So it's completely well-defined. That would be one argument. But of course, there are VMs that are well-defined too, maybe, but not as formally rigid, perhaps. So that's something that might matter too, that you want to be able to reason about code because you want some high assurance language underneath, right? So if you're writing what they call smart contracts, then you might be interested in having a solid foundation for that formally, to do better reasoning. That might be another argument, depending on how much you believe in that kind of thing. I guess those would be the main two. And then maybe the other is that it's also simpler and more universal than others, right? So you're not tied to a specific language ecosystem. You can pretty much define your own thing or import things that already exist in the wider WebAssembly ecosystem and do your pick as you want. You're not forced to use JavaScript or Java or something specific.
Mm-hmm. Makes sense. So should we, oh, one more unanswered question popped up. Here comes. The question is, how will gas usage in accounting be incorporated into the WebAssembly semantics?
So I can only say how we do it. So the startup I'm working for is one of these blockchain companies and uses WebAssembly. And the way we do it is we basically instrument the code and have mostly a fairly naive accounting function. So with a few exceptions, every instruction is just using up one cycle. So we talk about cycles, not gas. There are a couple, because most instructions are more or less linear time, or constant time, sorry. There are only a handful of exceptions like memory grow, which depends on how much you grow the memory. That is calculated differently. But other than that, yeah, every instruction counts one, and then the way the implementation works is we load the WebAssembly code. We do a transformation first that instruments it with a cycle counter. And basically at the beginning of every basic block, you kind of check against the balance you still have. So it's fairly straightforward, actually.
And after the fact, for those who don't know this terminology, my understanding is this gas business is just about bounding running time. Is that right?
Exactly, yeah. So it's a model for accounting for running time and also bounding it if you don't have enough cycles to pay for.
All right. Oh, and then John wants to clarify, this won't be part of the formal semantics of the language.
No, this is totally external, but something you can kind of complement it with easily.
Okay. So we have managed to empty the queue of questions. Should we do that poll now about what people want to learn more about?
Right. So for the rest of the talk, I kind of have two things, right, I could talk about. So I could either give an overview of the areas that the working group is currently working on, like the main proposals and what maybe the interesting problems are there, or I could give you a bit more my personal musings about the lessons learned and the difficulties of applying formal techniques from research into like a real world language project like that, what I learned from that and what was hard. So I kind of suspect that might be more interesting to this audience, but I don't know. So that's why I thought we could do a poll maybe.
I think the poll is now running and I'm showing it on the stage. People should be able to click to let us know what they'd most like to hear more about. Reminds me of election night. Okay, 14 votes so far. 15. Okay, unless there's going to be an upsurge of poll interest, it's pretty clear musings on lessons learned. So the second one is more popular.
Okay,
so there you go.
That's good, because the other one I've given too often. It's becoming a bit boring. I just to skip over these slides then. Okay, so this is fairly, like, it's not very structured here, just random thoughts I had and observations I made, and it's probably very subjective, but I hope it's interesting nonetheless. So kind of what you have to expect if you're interested in this, and if you're interested in applying your maybe some research you're doing and getting it into the real world somehow, right? This is very hard, and which doesn't mean I want to discourage you, but yes, you have to have certain expectations. So first of all, what you have to prepare for is there will be a lot of inertia and resistance in any such real-world project. So in general, when it comes to formalism, you will face a lot of skepticism, if not outright hostility towards it, because most of the people involved in such projects have a different background, right? So there's some culture clash going on there, if you want. And basically many view formalism as either useless or maybe even positively harmful, because they like hinder faster development cycles, which is not entirely untrue, right? I mean, it is a certain hurdle and it slows things down, but sometimes it's good to slow things down. But yeah, not everybody will agree with that, most definitely. So that is definitely one thing you have to be prepared for. And if you want to kind of get into that, I think it's almost essential that you, or at least somebody who supports you, has sufficient street credibility. So in a way, if you want to get something into such a project, it has to start as a sort of inside job, right? There has to be somebody inside the project who has the necessary street credibility, has worked on things like that before, who people believe has is competent to just judge these things properly. And you don't just need one such person, you actually need eventually backing from like at least the majority of key players, I would say. In every such project, there are a number of people who are kind of more, maybe not senior, but are more key than others because they initiated the project or whatever. So you need to be able to convince them eventually, otherwise it will also not work. Not all of them, but if you have several of them on your side and they really believe in what you're doing, then that is a big leap forward. I mean, there's a reason that you need that, and that is that the complexity of such projects and the sophistication they deal with in implementation is actually mind-boggling. So for me, coming from academia and then joining something like the V8 team to work on this engine, what completely blew me away. The amount of complexity going on there, the sophistication of the optimizations there, the tricks they are using, like many of them way out of any book I had known before, right? That's like so far beyond what you find in published papers, actually, that I was not aware of that, right? So it is really a kind of culture shock. And if you haven't worked on such a project before, people will just not believe that you are like knowledgeable enough to really know what you're talking about when you try to sell something to them. So there has to be something who is that knowledgeable, somebody. Sorry, and that, yeah, and while still working on V8, I can tell from my own experience that I've seen some papers published about like optimizing JavaScript, for example, like academic papers that even got best paper awards that were just entirely naive. And we're almost insulting in the way they suggest that they assume that this was not something that engine makers had already thought about. And you could just, as an engine implementer, some of this work you could not really take seriously if you knew what was really going on. So there is kind of like a disconnect from both sides often, right? So practical people not really valuing formalism, although they should, and like theoretical people not really acknowledging the sophistication of what's going on in practice. You have to be aware that usually these things are committee work, and with all the things that implies, right? So committees are really daunting, and it's not always fun to work in a committee. So you need to be really patient. You really need to be stubborn sometimes and not give in too easily. But all that requires a huge time investment and a large amount of frustration tolerance. So it really can be frustrating at times, and you make like no progress, and there are detractors that you really think are not reasonable at all, but somehow they convince some people, and you have to fight against that or argue against that. A significant amount of time investment is actually something that's not that obvious. So if it's like a larger project like that, there will always be coming in people with some ideas, and half of these ideas will be bad, right? Bad ideas. But not all these bad ideas will be identified by everybody as bad ideas. So you have to be kind of aware all the time that, you know, what are the current like pressures, what do people want, and maybe come up with your own solutions before somebody comes up with a bad solution, and then you have to fight an uphill battle for improving it or replacing it with something better. And that can be pretty stressful as well, right? To always stay on top of things. On the other hand, of course, you also have to be willing to compromise eventually, right? This shouldn't be no surprise. I mean, perfectionism doesn't really work here. Sometimes you will have to accept the ugly, just for practical reasons or because reality. And still, there will also definitely be blood on the floor at times. You have to be able to handle that as well, right? So it's not just frustration, it might actually be actual fighting going on. Depends a lot on the people involved and how reasonable they are, but my experience with committees, so I also was on the JavaScript committee before, there's always this one guy or two guys who kind of like mess up everything and cause like half the pain. So yeah, that's something that can be very frustrating as well. So, and when you try to get something in, you have to adjust to the audience. That means you have to be prepared to do a lot of explaining. So not everybody has the same background as you, and in this case, not everybody has the kind of formal language background, and things that you take like as totally obvious might not be obvious at all for other people there. So you have to explain a lot, and you have to explain like in terms of real world examples, right? So I have this problem very often that I kind of like just know something is conceptually a bad idea, right? But people won't believe it's a bad idea unless you translate that into something tangible, some real world example they can sort of relate to. And that is pretty difficult at times. It has often to do with finding the right terminology or using the terminology that people are using. So one example I always like to bring up is like, you know, compositionality, right? A language should be compositional. That's how we talk about it. But that is not something that's meaningful at all to layman folks, if I may use that term. They don't care, right? They want to write programs and they want to express this thing and that thing. It isn't really saying anything to them. But if you replace that term with kind of like, okay, if we do it this way, that's a refactoring hazard, right? That's something they will understand much better. So because they can relate to it. Oh, everybody has done program refactorings at times, and if I do that and something breaks, although it shouldn't, I'm just doing something in different order or something, then that's bad. So this is something, that's an example I actually learned on the JavaScript committee. I don't know who invented it there, but that was very helpful to talk about refactoring hazards, not compositionality. And there are other examples like that. And in general, it's important that you talk in text and prose and avoid Greek and fancy notation like the plague, right? Like any Greek letter you use will put off half the people, half the audience. Like with books. I think Stephen Hawking made this observation, right, in one of his books. And of course, ultimately, you have to be realistic, right? So with WebAssembly in particular, like I think having this amount of formalism in the language and the process was a big leap forward. And it's kind of like I would say a generational change, right? I said before we were kind of stuck in the 60s, and I still think that's true. And of course, as I said, I would like to go much further, right? Like having mechanization or something like that. But you have to like be realistic about what you can achieve in one step. And I'm really still today super surprised that we even got this far at all. So I would hope that maybe in another generation we can talk about mechanization, but I wouldn't hold my breath here. And finally, another thing that is important to consider is what's called the bus factor in industry sometimes. I don't know if people are familiar with the term. It means like the number of people that can be run over a bus before the project is dead, right? So, or a certain part of the project is dead. So with respect to formalization and things or features in general, that means you have to create a critical mass of people who can contribute to it, who can work on it, even if you're not available or something like that. So here it would be people with formal background. And the formalism WebAssembly, some proposals, it really wasn't that much of a big deal because people could adapt it just by copy and paste. But that isn't always the case, right? For some more intrusive changes, you really need some people who understand formal semantics and can do changes and additions to that in a principled way. And there's still always the risk of regressing this, right? So if suddenly, I mean, right now there may be 2-3 people who could do this on the working group, but if they were gone, I don't know what would happen to the formalization of WebAssembly, and if people would dump it eventually because there's nobody that can do it, right? So it really is important to consider this, that there is a big risk and that it might eventually die if you're not keeping up the energy or find others to to work on this. And I think that was kind of like, yeah, and we're out of time anyway. On last slide here. Summary slide. It's not really saying much interesting, but I thought I needed a summary slide.
All right, thank you. Yeah, so we are a little over time here already, but we could try to take any last questions. Let's see, did anything pop up since I last looked through? Nope. Andreas, are you going to be able to stick around a little bit at the end to talk to people in the lounge area?
Yeah, definitely. So I have to switch over to lounge, or how does that work?
Yeah, at the point where we make that transition, you would head to the lounge, but we can see if anyone wants to ask any last questions by this medium before we do that.
Mm-hmm.
Going once. We do have a question. Great. Now you can maybe see what the audience was seeing if you've moved back into AirMeet. How do you keep the language sane as you add extensions?
Yeah, well, I mean, that's what this process is supposed to guarantee, right? That you have to come up with all these deliverables. And of course, we have discussions and people will have opinions about something being sane or not. And you, of course, there's, to a large part, it's a social process. You have knowledgeable people there who will judge extension proposals. And often enough, people don't think it's sane. So proposals will be shot down. That's inevitable. And I mean, on the other hand, there will always be things that I, for example, might think is not a sane extension, or maybe not, maybe it's sane, but not really carries its own weight. So, or I just generally am not happy with it because it's so big or so unstructured. Like my favorite example maybe would be vector instructions. So recently SIMD instructions landed in WebAssembly. And that is just adding, I think, like 250 plus new instructions to the language just for this one SIMD vector type, right? And the pull request to merge this proposal was 100,000 lines, which includes all the test suite and so on. But still, right? Like, basically, it's probably 30-40% of the entire spec now, just for SIMD. And I personally, I'm not convinced that it's really worth it. But of course, there's a lot of pressure to support vector instructions, and they're also super ad hoc and like all this. So that's one example where your mileage might vary.
Okay. Well, I think this is probably the right point to close this session. Thank you so much, Andreas, for coming to tell us about this. And we'll look forward to the chance to chat with you in the lounge right after we close this session. People can click the clap button if they want to send some hands over the screen.
Yeah, thanks everybody for listening in.
Okay, I'm about to end the session. See you folks in the lounge.